All right. It's a great pleasure to talk to you. Hello from England. Today's presentation is about our work on developing electron microscopes that operate at a slightly lower than usual voltage. This is work I did when I was working in the group of Chris Russo at the MRCL in Cambridge. Alternative title of this talk is talk about cheap microscopes. Another alternative title is talking about cheaper and better microscopes, and hopefully I managed to convince you why cheaper can sometimes be also better. So let's take a step back, and before we actually talk about any microscopes, just consider if we are going to do electron microscopy on biological samples, what is actually the optimal accelerating voltage to use? Currently, most of the instruments use 300,000 electron volts as an accelerating energy. But why is that? And is this really the sweet spot? This depends on some properties of the interaction of the electrons with the material that we're imaging. And mainly on the elastic scattering, which generates your useful signal, relative to the inelastic scattering of the electrons in the material, which just generates radiation damage. And the two lines here, on this graph, the orange line and the black line show the probability of inelastic and elastic scattering, respectively, for an electron of a given energy inside a carbonaceous material, such as a biological material. And as you can see, these two vary slightly differently with energy. So the ratio is not constant. Therefore, if we construct this information coefficient, which is just the ratio of the elastic to inelastic scattering times some transmission penalty for the sample thickness, we plot it as the purple line for various thicknesses, we see that this information coefficient actually peaks at a certain voltage. And where it peaks depends on the specimen thickness. So, for example, if we consider a very thin specimen of only 100 angstroms or 10 nanometers thickness, the information transmission, so the unit of useful information you get out per unit radiation damage, is going to peak at some rather low voltage around here at around 20 electron volts, 20,000 electron volts. This is way lower than the commonly used 300,000 electron volts. If we consider a rather thick specimen, which is about 1,000 angstroms or 100 nanometer, which would be realistic, for example, for a fib milled section of a cell, actually the optimal voltage for the maximal information transmission turns out to be exactly 300 keV, which is what we mostly use. But how thick is the typical single particle cryo-EM specimen? Well, usually it's something in the low hundreds of angstroms. 300 angstrom would be a good approximation for most things, especially some larger molecules, but usually it's 300 angstrom or sometimes even thinner. And if we calculate where is the maximal information coefficient for a 300 angstrom thin sample, this actually turns out to be at around 100 keV, not at 300. So if you're operating at 300 keV with this specimen thickness, you're getting slightly less information than you would be getting at the lower voltage per unit radiation damage that you do. So based on these measurements and these calculations, we were actually convinced that for single particle cryo-EM, it is beneficial to work at a lower voltage. There is another way to replot this data, which is find the location of these peaks for the different specimen thicknesses and just make this graph of what is the optimal voltage for a given specimen thickness. And here the black line just shows the region in which we actually did the measurement, and everything else with the dotted line is extrapolation based on theory. So you can see that when you get into the thick specimens, which is typical for like tomography, cell sections, it is beneficial to work at higher voltages. But for the typical cryo-EM thicknesses of a couple hundred angstroms, actually some voltage around 100 keV should be even better. Based on this work that we did now more than 5 years ago, we wanted to actually demonstrate this with the real biological specimens. Turns out to demonstrate it, we need to construct the appropriate microscope that operates at this low voltage, but also satisfies all the other requirements for a TEM used for biology. So we actually went back to the drawing board and considered, if we're going to make a new microscope, what are the absolute necessities that we need if we want to use it for single particle cryo-EM? What are things we absolutely cannot give up on? And let's just remove all the other unnecessary features to make this most simplified instrument. So we came up with this list here. Firstly, we need a coherent source to be able to generate phase contrast. This means the source needs to be a field emission gun. It needs to be fairly stable and have a fairly low energy spread, and it would be sufficient for it to operate at 100 kilovolts. Then for a condenser system, 3 condensers or lens system is obviously nice because you can generate parallel beams, but 2 condenser lens system is sufficient. We have some strict requirements on the stability of the specimen stage and on the vacuum specifications of the chamber so that we can preserve our cold specimens free of contamination when we load them into the microscope, and so that they do not move too much while we're trying to acquire our images. For a single particle cryo-EM, we don't really need the large tilt range of the stage. That actually simplifies the design. And crucially, we need a small objective lens with a good information limit and a rather low chromatic aberration, which we're going to talk about later. Finally, probably most importantly, we still need a very efficient electron detector, because that is the main thing that will determine whether the actual images produced will be good or not. And the detector technology has advanced a lot, and this has been crucial in unlocking the potential of cryo-EM. So we need to have a detector that operates at the voltage of this microscope, but also has a good efficiency all across the different resolution ranges, is capable to perform electron counting, and ideally runs at a fast frame rate. So with these requirements, we went on and designed a microscope. And then we searched for how are we actually going to make it and who's going to make the different parts. So in the end, what we came up with is a combination of different manufacturers and put together here at the LMB. For example, we developed a new field emission gun that is made by a company in England called York Probe Sources. This field emission gun operates only at up to 100 keV. Which simplifies things quite a bit, actually, when you don't need to go all the way up to 300 keV. The whole microscope is built around a JOL 1400 column, which is fairly inexpensive in itself, with a high-resolution pole piece. You will see that we used some commercial side entry folders from Gatan, and in the proof of principle work, we use this JOL microscope stage as is, but we also have a project where we're developing an improved prototype of a stage here at the LMB. And finally, for a detector, we used the detector from Dectris, which is a repurposed detector that was originally developed for detecting X-rays, but actually it turns out is pretty good for detecting electrons with energy at around 100 keV. It has a very fast frame rate of around 3,000 frames per second and very high detective quantum efficiency, which is what we wanted. And from drawing, we managed to get the actual instrument within a few years with the great help of all of our collaborators. So here you can see the gray piece on top is the field emission emission gun made by your probe sources. The detector is single detector is at the bottom, and everything is built around this fairly simple GRL 1400 microscope. Just a quick side note, this is a part of our cheap cryo-EM lab. We have 3 of these microscopes sitting in one room, separated by these curtains. As you can see, they don't really require a lot of space. They're not very tall, so they fit in some more standard rooms. And we're also working on tools for cryo-EM sample preparation that are also cheap and accessible. And for example, here on the side, you can see this chamber with the blue box. It's actually a manual plunger for freezing grids, which is also built in-house by our mechanical workshop, but the drawings for these are available, and there are drawings available from others as well as a E10 cryostat for the plunger. So you could, in principle, have all of this equipment, your sample preparation, glow discharge, plunger, microscope in one room, and have your sample preparation and screening right next to each other, which is really convenient, makes things fast. And also all of these things are individually much cheaper than the kind of top-end commercial stuff. So now we're going to take a slightly closer look at this microscope and its components and what can it do and what is special about it. So here we just have the simplified diagram and zoom in into the components that were most crucial, starting with the field emission gun. As I mentioned, going up to only 100 kilovolt is technically quite a bit simpler than going up all the way up to 300 kilovolt. And for example, this eliminates the requirement of using sulfur hexafluoride gas inside the FEG, which makes it simpler to maintain and also cheaper. Then here we have the cross section of the objective lens of the microscope, which and this is the pole piece gap, and this is the gap where the specimen stage would be. And finally, we have this dexterous detector. Now we're going to talk a little bit more in detail about the objective lens. And a question that arises quite often when we talk about the low voltage microscopes is, well, if we already have a microscope operating at 200 or 300 keV, like a Glacios or a Cryos, should we just turn down the voltage on that and operate it as a more efficient microscope? And the simple answer is no, because actually the technical requirements for the objective lens and the detector are fairly different for these different voltage microscopes. So what is special about the objective lens that we need? Well, because we're operating at the lower voltage than the traditional 300 keV microscope, actually any energy spread in the source as a fraction percentage, so the energy spread relative to the primary beam of the energy, primary energy of the beam will be more. Therefore, we will accumulate more penalty from the chromatic aberration of the lens. So the chromatic aberration of the lens is just its ability or inability to focus beams of slightly different energies in exactly the same way. And because of this chromatic aberration and the inherent energy spread of the electrons that come out of the source, we get this envelope function that dampens the high resolutions in our image acquired through this lens. And this is more severe at the lower voltage because this denominator here becomes smaller. And to compensate out for that, we actually ideally need a lens with a smaller chromatic aberration coefficient than you can get away with at 300 keV. The chromatic aberration coefficient is directly related to this size of this gap between the two pole pieces and the lens. So basically this space where your specimen and your stage fits. So to achieve a smaller chromatic aberration coefficient, you have to make this space tighter in your lens design, which is definitely doable, but you need to be careful about that. And also, if you really want to make this space very tight, to make the chromatic aberration coefficient very small, you will have to give up on specimen tilt because just physically there is no space to do tilt in this little gap. And now moving on to detectors. So detecting 100 keV and 300 keV electrons is also very, very different. And this can be illustrated if we look at the tracks of such an electron when it scatters in the material of our detector, which is mostly, in most cases, just silicon. So if we look at the path of the 300 keV electron in a piece of silicon, all these different squiggly lines are just the simulated trajectories of the electron possible through this material. And the electron needs to scatter from quite a couple hundred microns in the material until the electron loses all of its energy. That would be problematic, right? Because then all these tracks spread over a large area. So the way we worked around this previously, when the detectors for 300 keV were designed, we made back-tin detectors so that the piece of the detective material, the silicon, is only a couple tens of microns thick, and the electron trajectories do not have a chance to spread out too much, but still the electrons do deposit some energy, and you're just detecting in this little red triangle. So the spread is reduced because you're only scattering through a thin piece of material. However, if you wanted to apply the same trick for the 100 keV electron, you realize that this is not really going to work because the 100 keV electron is going to scatter much more frequently in the material, and it's going to lose its energy much faster. So it's not going to make these long tracks. Instead, already within this little thickness of around 30 microns, it's going to scatter multiple times and make these quite spread out tracks. So then the design of the detector becomes slightly different. You don't have to make the detective layer, so thin, and you kind of commit to detecting the entirety of these trajectories. And instead, you also have to make the pixel laterally wider, so you can allow for this spreading of the electron trajectories. And this detector, single detector that we used in our demonstration, has exactly this type of a pixel design. It's a hybrid pixel detector, which also makes it conveniently very radiation hard and very fast. It is capable of electron counting, like the direct electron detectors at higher voltages, and it is even capable at super resolution localization, which is based on the activation of neighboring pixels, guessing where exactly did the electron land with some sub-pixel precision. And the DQE, which is most important feature of the detector, is pretty great. It's almost as good as it can get in theory for a pixelated detector. So it's around 100% efficient at zero frequency and more than 50% efficient at the Nyquist frequency. So it's a really good detector. This is just an image of to show you the ultimate capabilities of the 100 keV microscope, and showing you that, yes, you can see atoms with this microscope. Here we are imaging a layer of gold, so very thin gold crystals in a particular orientation, such that each of these white dots is an actual atomic column. And you can see the atomic columns in the direct image, which is pretty good. And also you can see the reflections in the Fourier transform of the image up to around 1 angstrom, which is roughly the resolution limit of this microscope. After this, we were quite happy with this instrument that we managed to build together, and we went on to actually demonstrate its performance on some biological samples. We chose a variety of proteins that we had worked on in the past, or our friends had worked on in the past, or some that were slightly new to us. And we managed to solve all these different structures that I'm showing here using this microscope within the span of a couple of weeks. And they range from about 200, slightly less than 200 kilodalton in size to more than 3 megadalton in size. And they include soluble proteins as well as membrane proteins, proteins from bacteria as well as human proteins. All of this worked really nicely. And all the resolutions of the different reconstructions are in the 3 to 4 angstrom range mostly. I'm just going to focus on a subset of these, just to show you how this microscope can be useful, for example, in some early stages of some projects. and even not so early stages. So for this, we decided, let's try to look at some proteins that we ourselves have never looked before. So we just went on our gene and chose 3 plasmids that encode the following proteins: GAPDH, glutamine synthase, and aldehyde dehydrogenase. We ordered these plasmids, we expressed these constructs in E. coli, and we used affinity purification to get these proteins. We cleaned them up by size exclusion, and then we just froze 1 grid of each, and we had a look in our microscope, and these are the micrographs that we saw, and you can already see that the 100 keV micrographs look way more contrasty than the 300 keV micrographs. That's because of this increased scattering of the lower voltage electron beam. So that's nice, because for screening you can like really see your particles properly. We went on and collected a really small data set manually in this case, because we had not implemented any automation yet, of 400 movies for each of these samples on this microscope. So basically that's a day of manual data collection on each. These are the 2D classes that we obtained from these data sets. By the way, 400 movies does sound like a lot, but actually, because the detector is only has 1000 by 1000 pixel, which is 1/16 of the area a commercial 300 keV detector would have, this is kind of equivalent to way fewer movies that you would acquire with some normal settings on a 300 keV microscope and larger detector. And from this really small data sets, we managed to obtain these 3D reconstructions. Quite interestingly, for 2 of the samples, the aldehyde dehydrogenase and the GAPDH, the actual resolution that we obtained, slightly under 3 angstrom, is actually better than the Nyquist limit given by the 2 times the pixel size at which we collected. So this is only possible because our detector had this capability for super resolution localization. So even though you are collecting with a pixel size of 1.65 angstrom in this case, so your Nyquist limit would be 3.3, but you're doing these super resolution tricks. So actually your super resolution pixel size would be 0.8, and you have the chance to recover this information that is way past the Nyquist frequency. And we were really happy with all of these reconstructions. And I think this really showcases that these simple instruments can be used to look at a variety of different biological specimens and reach these resolutions around 3 angstrom, which are already very interesting for atomic model building, for finding bound ligands, and really for quite a lot of the stuff that we might want to do in the lab. We are not the only ones that are working on popularizing the low voltage cryo-EM. There are a few other groups. For example, the groups of Gabe Lander and Klim Verba in California have recently published this case study where they used a 100 keV microscope with a field emission gun, and they also obtained some really nice structures at 3 angstrom resolution and better. They also used the GATAN 626 side entry folder like us, but they used a different detector, which is the GATAN Alpine detector from the same manufacturer that makes the K3 detectors, which is also specifically designed for 100 keV. Even more recently, another study from an Australian group was published, which is slightly different because they use a microscope that does not even have a field emission gun. Instead, it has a lab 6 source. There you have to take an even bigger penalty for energy spread and climatic aberration, because the lab 6 source had a bigger energy spread than the field emission gun. So even though you're fighting against a faster decaying envelope function of your images, you still can obtain pretty nice reconstructions of a test sample like apoferritin, but even better of a GPCR, which is already quite a challenging target in itself, and a rather small one. And this microscope was also used with the GATAN Alpine detector, which is developed specifically for 100 keV. So now there is a variety of these instruments. You can have the gel instrument, you can have the Thermo Fisher instrument, you have a choice of detectors. They all operate at keV, and really we expect that in the next few years this is going to take off. There's still things that can be improved. For example, larger detectors with more pixels would make everything easier. Lenses with smaller chromatic aberration would also make everything better. So the improvements are possible, and we expect that when all of these are actually implemented, we will be able, with lower voltage and cheaper microscopes, to actually achieve better results, not just on par with the 300 keV expensive instruments, but actually better. So we're still working on these improvements. So this is how we imagine the future of the cryo-EMs. We expect that every lab around the world or every pharma company will be able to have the robust, low-cost 100 keV microscope capable of reaching resolution around 2 angstrom routinely. Then there, of course, there will be the high-end microscopes that will be mostly at the large facilities or the shared facilities. They will be capable of reaching high resolution with more speed and more automation, but kind of really an elite instrument. And finally, there will be a whole separate class of instruments for imaging cells and thicker samples, which require much more technological innovations than those simple instruments for single particle cryo. All right, so I think with that, I'm going to wrap it up. I'm going to thank all the people that we worked with on this project, including Greg McMullen at LMB, who basically put together the microscope and the detector. This project was led by Richard Henderson and Chris Russo, who was my former supervisor. And a lot of these samples that I showed you were purified by Dani, a former PhD student. All right, and thank you for your attention. And I think I still have a few minutes to take some questions.
Thank you very much, Katerina. So that was a really inspiring talk. It must have taken a lot of patience for those Australian people to collect the data on a Lab 6 instrument. Did you speak to them?
No, actually, I have not. I have not had personal contact with them, but I recommend everyone to have a look at their preprint on bioRxiv. Yes, it takes a lot of patience. I think they did have automation on this microscope, which makes it slightly less painful. But still, yes, you need to get more data to compensate for the slightly lower quality. But it is interesting in itself that it is possible at all to use such an instrument.
It is very interesting. Okay, so does anybody have any specific questions for Katerina? Everybody? Homer? No. Jeremy?
Yeah, I can. Oh, thank you. Great. Hi, Katerina. That was a great talk. Just have one question. It's to do with the software. So when I spoke to Richard Henderson about this project, he said one of the kind of things that could make it possible is that the software could compensate for aberrations that get included by having a really cheap microscope. Could you maybe just sort of talk about, whether that's actually been the case, because this was a very long time ago, or whether those aberrations have not actually been a problem?
Yeah, that's a great question. Thank you. So one aberration that we absolutely cannot compensate for in software is the chromatic aberration, just because all of these electrons at different energy cannot later on be distinguished from each other. However, for things like spherical aberration or beam tilt, anisotropic magnification, and some higher order image distortions, these days, actually, when you do your image processing in Reliant or other software, if you at least can get to initial 3D reconstruction, later on you can start to calculate and compensate out for these aberrations. So for example, this sort of microscope without the box naturally is less stable in terms of its beam tilt. So as you're acquiring data, you may accumulate some beam tilt during your session, or you maybe even start out with some more beam tilt than would be normal. But this kind of aberration these days can be compensated for in the processing. Actually, in the data sets that I showed you that we processed, in some of those we had quite a huge beam tilt, probably because the microscope was not properly aligned at the start of the data collection, so something like 1 milliradian, which would be outrageous if you're not compensating for it in software, but because you can, it's not a problem anymore.
Okay, thank you very much, Katerina. I'm going to call on the next speaker, Jeremy.
Thank you.
Should I just keep the mics?